Today. He has picked Friday the 13th, a day on which space debris is supposed to impact the Earth. I don't know if you're hoping the Earth will explode or to defend his thesis, but this is a project that is part of a 4-year NSF project to try and understand the initiation and early development of low-angle normal faults. And James has done a lot of work, a couple weeks in the field, and a lot of work characterizing pretty complex samples and then trying to use stable isotope techniques to understand water-rock interactions moving along the fault during this early history. So thank you very much for coming up today to give this presentation to us. We look forward to seeing it. Without further ado, I'll let you take it away.
All right. Today I'm going to discuss the work I've done to characterize fluid mobility and thermal structure along a Loyola normal fault in the Mojave Desert. I'll start the presentation off by giving some background on Loyola normal faults and their significance. I'll talk about the methods I use to understand fluid involvement and introduce you to my field area, and then get around to discussing my results. So Loyola normal faults are large regional features that are found to accommodate typically over 50 kilometers of displacement due to the relatively shallow angle of dip. The model for their formation would be the bookshelf or domino effect of the upper brittle crust due to the extendal ductile crust, where a plane of weakness evolves along the base of the brittle crust. Stable isotope studies have shown that these faults can be major conduits for fluid flow. So why are we interested in Loyola normal faults? Loyola normal faults contradict Andersonian fault mechanics, where a fault would or should slip at 60 degrees. So other things are invoked, like rotation of stress angles, and modern seismic studies have shown that these faults lack large magnitude earthquakes. So possibly they creep along. This invokes ideas of increased pore pressures, fluid overpressures at the mid-crustal depths, and the development of aligned biosilicates that could help to contribute to that fault slip. So the goal of my study would be to see if fluids were present along a Loyola normal fault in its early slip history. In 1998, Morrison and Anderson proposed the idea of footwall refrigeration, as they found an extreme thermal gradient using the oxygen isotope thermometry within 50 meters below the damage zone of the Whipple detachment fault. They proposed this through the rapid advection of heat along the detachment zone through the introduction and circulation of cold surface-derived fluids. Some possible complications from previous stable isotope studies of Loyola normal faults would be the bulk geochemical technique typically used, where a milligram sized sample from coexisting whole minerals are picked and analyzed through laser fluoridation. Within the past decade, more spatially resolved techniques have shown that isotopic heterogeneity can be typical of grain size at grain scale within these fault zones. So here's a schematic of showing just diffusion within grains from core to rim, and re-equilibration of grain boundaries, and a combination of those effects with cracking and veining involved. So a bulk geochemical technique will take the average of all these events rather than giving you a specific event that a more spatially resolved technique could give you. So to avoid this, I'm going to use SIMS, or a secondary ion mass spectrometry, which uses the intensity and charge of secondary ions to give you compositional information. This is a schematic of the Kamika 1280 I used at the Wisconsin Sims Laboratory, where a positively charged cesium primary ion is shot as a sample using a 10 micron spot diameter. That liberates negatively charged oxygen isotopes, which are focused around mass spectrometer and separated into oxygen 18, oxygen 16 isotopes. So here I am at the Kamika 1280 Wisconsin. Here's an example of the spot size with the 10 micron diameter. You can see this is a very large instrument. It's in a room about the size of this one. And you can also see the many maps that are involved with doing this type of analysis at the micron scale. So again, my research aims are to examine another low-angle fault using a more specially resolved technique to analyze oxygen isotopes and determine if fluids were present during the early slip history of that low-angle fault, and if so, can the fluid source be constrained, and what effects that fluid may have on the thermal structure along the fault. So to do this, I will focus on the well-mapped and well-exposed Mojave Wash Fault in southeast California. It's a centrally located feature of the Colorado River Extensional Corridor, which was found to undergo extension 23 to 12 million years ago through Argon cooling ages. A simplified geologic map of the Chemehuevi Range, shown here with the Mojave Wash Fault, where exposed to the surface outlined in bold, the regional Chemehuevi detachment system on the margins of the Chemehuevi Range is shown with the dash bold line. Cretaceous granite diorite makes up most of the southwestern portion of the range, and Proterozoic gneiss in the northeast. The regional extension direction is shown by this arrow to the northeast. Sampling sites by Ohio University over the past few years are shown by these stars. Vertical transects highlighted in this study are shown by the yellow stars. Also, you can see the relatively close proximity to the Whipple Mountains, where the extreme thermal gradient found by Morrison and Anderson took place. So here we have the cross-section of the area, where you can see the Mojave Wash Fault within the footwall of the regionally extensive Chemehuevi Detachment Fault. This fault is thought to have a relatively slow or small displacement, around 1 to 2 kilometers. This is primarily found to be the case through the complete lack of fault gouge within the fault, as well as some offset markers. Another reason to study here is a comparison to a previous thermal structure study done by John and Foster in 1993. They found an increase in temperatures towards the northeast, so increasing paleo depth to the northeast, using ages and cooling temperatures of coexisting biotite, hornblende biotite, and potassium feldspar, as well as tight fission tract data. Now I'll get into describing the vertical transects. I'll start in the vertical transect in the southwest, known as the saddle. The host rock here is Cretaceous granite diorite. This is an overview of the saddle area where the Mojave Wash Fault damage zone is found to be around 40 meters thick. You can see my sampling locations shown by these yellow pins throughout the footwall and the damage zone. This is a photo of the base of the damage zone, where it's highly friable chlorite breccia with some localized cohesive cataclasites. Here's an example of one of those cataclasites where you had a very fine-grained purplish matrix with fragments of the host rock within it. Within the footwall, there are some additional offsets. Here's an offset around 20 centimeters over a 1 centimeter thick shear zone. And just a comparison of once you get out of the main damage zone, both the footwall and the hang wall are both quite cohesive granite. This is important to note that there is no pre-existing fabric here that could help facilitate slip over time. looking at some of the microstructures from the saddle, we have just the rock samples on the left, elemental X-ray maps done by CM in the center, and backscatter electron images with some minerals identified by energy dispersive spectroscopy, right there. Minerals in these shear zones were identified to be primarily quartz, potassium feldspar, and epidote, with an extremely fine grain size of typically less than 10 microns throughout the shear zones. This was a complication for doing analysis in this vertical transect due to the ion microprobe having a spot size of 10 microns. So now going to the northeastern portion, that Cave Wash vertical transect, where the host rock was found to be Proterozoic gneiss. Here's a sampling overview of the Mojave Wash damage zone transect, where it's found to be primarily, again, chlorite breccia with some localized vein fill, primarily with quartz and epidote. We ran out a sampleable footwall in this area, so we walked just down the wash to where the footwall was better exposed and started sampling again. In this area we found what we interpreted to be in the field to be a Mojave Wash fault splay. This feature was found to run continuous underneath the main Mojave Wash damage zone, and we did not find this to cut the Mojave Wash fault in the field. Here's a photo of that feature. It's around 1 meter thick. So some of the microstructures of that Cave Wash. Again, it's primarily quartz epidote rich veins. Surrounding the veins, there is a lot of quartz epidote chlorite intergrowth among the gneiss fabric. The grain size here was larger than what was found in the saddle. It's still quite fine grain, around 10 to 100 microns, but that's good enough for ion microprobe work, so we got a lot of good data from that Cave Wash. This is a summary of all the analyzed samples. There's 23 by ion microprobe. The corresponding color to the sample number corresponds to the color of the sampling site here. So you can see primarily we focused on the vertical transect of the saddle region and that Cave Wash region. Giving a given shape, each sample represents a given analysis of a given mineral. The oxygen isotope standard UWQ1 is in the center of each sample, with all unknown analysis all taking place within the innermost centimeter of the sample due to analytical reasons. So before I get into discussing our results any further, just a little primer that I'll use the oxygen isotope, the normalized fraction delta O18, which is just the ratio of oxygen 18, oxygen 16 of the unknown sample compared to the standard. And a little background on the oxygen isotopy. In this study we used quartz epidote mineral pairs, which were found to be in equilibrium. So were interpreted to be in equilibrium. So to get temperature from this, you basically take the absolute delta 18 value of quartz minus epidote, and that gives you the capital delta, and the capital delta 18 of quartz minus epidote gives you the temperature due to the experimentally determined fractionation between those two minerals. Going through the results can be quite complicated due to the hundreds of spots of analyses, but I'm going to walk through all the analyses of the saddle region here, where quartz analyses, all analyses of a given sample are just arbitrarily arranged in increasing delta value. Quartz analyses are shown by blue circles, epidote is yellow triangles, and potassium feldspar in purple crosses. With the colored tie lines here are what were analyzed to be quartz epidote mineral pairs with the capital delta between those shown. Analysis by SIMS found the host magmatic quartz values to range between 9 and 10.5 per mil. The H above each analysis denotes analysis within the host zone of a sample. The C above a given analysis represents a core analysis within a grain. So here we have cores within this magmatic host range. So this would be interpreted to be a host class within a shear zone. But here you also see very high quartz values without any of these notations. This actually comes from a quartz-rich vein. So looking at this data can be quite complicated, so it's good to give a petrographic relationship to the austenite-stope signatures. So when doing this, you do see here that analysis within this granodiorite host gives you the high delta 18 values, whereas within the shear zone gives you much lower delta 18 values in both quartz and, in this case, potassium feldspar, interpreted to be from the influence of low delta 18 values from surface-derived fluids circulating throughout the fault. Similar results are from this sample, where analysis from the host give really high delta 18 values. But also to note that within the same host zone, you get relatively low delta 18 values through the analysis of a rim. This orange denotes the rim analysis. So this would be a grain boundary that really equilibrated with the external fluid. Here you can see this quartz-rich vein with the high delta 18 values. This sample was taken deep within the footwall of the Mojave Wash, so perhaps an area of very low fluid flux. So just a summary of all the analysis done in this study. I'm not expecting you to take anything away from this other than perhaps noting that some samples do give quite consistent values across the board, while as others give quite a range within a sample. So trying to give more meaning to this range, methods were followed by Ferry et al. In 2010, which looked at ion microprobe data to try to understand the heterogeneity. They used the 2 standard deviation analytical error of a given analysis and compared that amongst populations within a given sample. So if they found a population within a given sample to have greater than 95% confidence interval, they deemed that to be a homogeneous population. Lower than that 95% confidence interval, heterogeneous. So when that was done, heterogeneous samples were determined. Here we have quite a large variation from one population within this sample. So here you see a variation of around 5 per mil in quartz and 4 per mil in epidote, as well as large variation in quartz epidote mineral pairs, where the capital delta seemed to be around 13 per mil to 5 per mil. So this would be an example of a heterogeneous sample with grain scale isotopic disequilibrium, and we did not use heterogeneous samples for calculating quartz epidote temperatures. But as for homogeneous samples, so here we also see again quite a range variability within a given sample, but when broken into different populations, we see that a given population is found to be quite homogeneous, no larger than a per mil difference in this case. Except one exception, in the center of this quartz epidote-rich vein, we do have 2 core analyses from this grain, consistently around 9 per mil, where the rim of that grain gives consistent values around 3 per mil. So ignoring these core values, as they are not interpreted to reflect fluids moving throughout the fault, this would be a sample that would be used for quartz epidote oxygen thermometry. So coming back to the idea of looking at variations across the fault through vertical transects, as well as along the fault through different sampling depths. Now I'm going to discuss some of the calculated delta 18 of the fluids. When you do have in this case, epidote and triangle, quartz and circle, when you have a quartz epidote mineral pair, you can calculate the delta 18 of that fluid that precipitated them. The blue vertical bar here represents magmatic quartz values. The green vertical bar represents magmatic epidote values. The horizontal black bar here represents magmatic delta 18 calculated water values, and meteoric values for water at the Chemehuevi latitude are around -5 per mil. And in between these two, we have the brines and hydrothermal fluid exchange to be -5 to 5 per mil. So we do see calculated delta 18 fluid values coming near this surface-derived fluid signature. One sample in particular did give calculated delta 18 fluid values to be in magmatic equilibrium. This sample is clearly from a fracture of quartz epidote vein. This is interpreted to be possibly the very early fluids before surface-derived fluids could ever get involved with the fault. So now looking at the actual vertical transect sites, here we have the saddle, the relatively shallow area. Previous sampling site done by Ohio University of Mojave Wash sampling site, and the Back Cave Wash. Quartz values are shown in circles and epidote in triangles. The black data is data by the Morrison and Anderson study in the nearby Whipple Mountains. The blue vertical bar in each transect represents quartz magmatic values, and the green vertical bar represents epidote magmatic values. But what you see consistently across vertical transects is a shift to lower delta 18 values in both quartz and epidote within the damage zone at the given site. Some variability is seen within the footwall Back Cave Wash. This is interpreted to be due to that observed Mojave Wash display. So now getting to temperatures calculated from the quartz epidote mineral pairs. The red bar in each of these is the ambient footwall temperature found by John and Foster in 1993. But you see a consistent shift to colder temperatures in each of the vertical transects, decreasing towards the Mojave Wash fault damage zone. But in the saddle area, we do see relatively higher temperatures than the ambient footwall, and in the deeper portions of the fault, we see relatively colder temperatures compared to the ambient footwall temperature. So when the data is shown with distance along the fault, so relatively shallow areas of the saddle and range front sampling sites, where in relatively deep areas of the Back Cave Wash, Mojave Wash sampling sites. The blue bar here represents the ambient footwall temperature found by John Foster, and the red dash bar represents the mean calculated temperature at a given sample site. See that these do not match up well. So with an assumed initial dip of the Mojave Wash fault of around 25 degrees, we can calculate paleo depth. Here we have the Back Cave Wash and saddle vertical transects. An assumed thermal gradient within this regional extension zone of 35 degrees per kilometer. Compared to that assumed geotherm, we have much colder temperatures at depth, much hotter temperatures in shallower portions. What could possibly cause this? I think that the presence of many syntectonic dikes could be a possibility. Here we see in Backcave Wash dikes with intruding in some cases into the damage zone of the Mojave Wash with lineations parallel to the regional extent of 050. As well as a single temperature calculated from a quartz epitope mineral pair from the margin of this 1 meter thick mafic dike gives a temperature of around 950 degrees. So it's interpreted that these dikes could influence the temperatures along the fault, as well as potentially helping drive some fluid migration. This can also be seen in other studies. Here's an example from Keg et al., where hot fluids are seen pumped up oceanic detachment fault with the melt winds heating it from depth. Models by Picardi et al. Show colder temperatures within the recharge zone of a detachment, whereas hotter temperatures in the discharge zone of the detachment. So relatively shallower temperatures compared to relatively deeper temperatures. So in conclusion, fluids are thought to have circulated through the Mojave Wash Fault with calculated delta 18 fluid values as low as 5.7 per mil. Surface-derived fluids, either meteoric or brine, are seen at depths of up to 11 kilometers. Grain scale heterogeneity does complicate isotopemometry in fault rocks. This study is a good example of why more spatially resolved techniques are needed to do this type of work. Heat and mass transfer along the Mojave Wash was found to create both a vertical thermal gradient and horizontal vertical gradient along the fault. This was to be consistent with the Morrison-Anderson model of footwall refrigeration. The evacuation of heat from fluids and dike emplacement could influence the heat transfer along the fault. So, with that, I'd like to thank Craig for all his help over the past 4 or 5 years since I've been. Craig McDonald, he was a student right before me working on this project. He was a very big help. Barbara John, Justin LaForge at the University of Wyoming are our main collaborators. National Science Foundation and the Geological Society of America providing funding for this project. The labs at the University of Tennessee and the University of Wisconsin, and everyone at the department here at the University. Thanks.
So